Let us illustrate that by using 3 spice tools: WinSpice, PSpice, and switcher CAD. Let me first, using the text editor, and open up the code to be opened up by WinSpice. And this is the first one, where all the 4 input is 1 volt DC. So we're invoking the OpAmp1 sub-circuit, which is to be included right here. We call it OpAmp1 Live. These are the components based on the Revansik technique, and we're using the WinSpice 3 command. The second circuit is basically the same. We only change the last 2 input to 3 kHz and 2 kHz 1 volt amplitude apiece. Now let us open up WinSpice program. File, open, the first one, right there, 5 volts. The second one with 2 sine input, that is the output. Next, let us use the PSpice. I will use the PSpice Design Manager. The first navigator icon is for schematic. The second one is for the PSpice AD. I'll file open the circuit. That is this one here. You can of course view that or just run the open up file and view the simulation result. At the trace, select the output. That's that. Now let us this time activate Open Schematic. So our schematic is OA schematic right there, where the OpAmp library has already been included, and this one is the supporting library for the resistor, sources, and so forth. Each one of these has already been set up to 1 volt a piece right here, and this is the sinusoidal. Let me just run the simulation right there. Finally, let us try doing it using linear technology switcher card number 3. I will first open the circuit. Happen to be the same pspice netlist as used by pspice. It also invoked the probe command. We're using the eCenter library. Click Plot Setting, Visible Traces, select Vout. That is that. This time we open up a series of schematic version. This is the one that will be using our eCenter Live. So here I have the symbol. The symbol we have here is, of course, that symbol. And it is invoking the library subcircuit name of OpAmp1, which is in that list, similar to the one we saw earlier. So now we can run this, but let me remove this symbol to conserve some display screen space. Probe the output, that is the result. Next, let us also open up a file using an LTC one-pole based on the universal operational amplifier. We'll use level 1. They got quite a few, level 2, 3A, 3B. This has an open loop gain of 100K, gain bandwidth of 10 megahertz. And of course that is the symbol they use. Let me remove the symbol. Now let us execute this. From the output, same result. Next, a series of symbol pointing to schematic. This is the one using LTC, this is the one using eCenter model, the OA multiple. So we got two here, one using eCenter schematic, one is using the linear technology. Let me use the one from eCenter. So we have created here a symbol. And we have created here, that symbol is pointing to this schematic. So based on the eCenter subcircuit, we created here a schematic where the output, the input here, controlling this voltage source that produces 100K times across 3 0. And from 3 to 0, there's a series RP1, CP1, and the voltage across CP1 is the controlling voltage of the E buffer that produces 1 volt, output resistance of 10 ohm. So that is our symbol, and the rest is the same as in the other previous circuitry. Let us probe the output. Right there. Finally, let us open up a schematic that uses LTC copyrighted one-pole model. This one here. So we have a new symbol here. We call it OpAmp LTC one-pole. Let's open up the symbol, which is that one. Open up the schematic, it encapsulated. This is the very simple copyrighted one-pole model. It only uses one current generator that's controlled by the input across node 1 and 2. It produces a current gain of 100K that is injected into our 3C3 combination. And using the 100K and 10 meg gain bandwidth, we can calculate the capacitance. Turned out to be 1.5915 millifarad. Let us run the simulation. Probe the high-level output. Exactly the same result. Okay, that concludes this quick demonstration.